Recording. Welcome to the Cloud Robotics Working Group. Today will primarily be around Julien's talk. Julien's here as a guest speaker. Thank you for joining us.
Thank you for inviting me.
Absolutely. And I don't think there's any reason to wait around. Please take it away.
Yeah, okay. Let me share my screen now. Okay, sharing now. Do you all see the screen?
Yeah.
Okay, so today I will talk about Eclipse Zenoh and what it can offer for cloud robotics. But at first let's have an introduction on what is Zenoh for those who don't know yet or never heard about Zenoh yet so far. So we have a nice dragon as a logo, but mainly Zenoh is moreover a protocol. And it's a protocol that we say is a pub/sub query protocol that unifies data in motion, data at rest, and computations for embedded microcontrollers up to the data center. So that's a long sentence, but let me expand a little bit on this. So our background as a team of Zenoh developer is really middleware for distributed systems. So we have a very long experience on this. Moreover, with DDS, we have a long experience with DDS implementation. Our team is also implementing Cyclone DDS. And with all the experience we have, we realize that in some use cases, there is a need of different patterns of communication, right? Pub/sub, of course, is one of the patterns that you have in distributed system, which is very nice because it allows a lot of decoupling between all your applications. But still, queries are something which is also important. I say query, which is something we consider rather different than request and reply, but you can see it as request reply. In our mind, a query can go to several servers at the same time. For instance, if you query a database, it could be several replicated database. You can have a single query which can go to several different servers. So we need a pattern to send different queries, queries to different targets and to get different replies for a single query. That's why we made a new protocol to support this, already built into the protocol, rather than to have request reply mechanism built on top of pub/sub, which can come with a certain drawback. So we felt better to implement this directly in the core of the protocol. So Zenoh by itself supports those main two pattern of exchange for distributed systems. And it unifies data in motion, data at rest, and computation. Why? Because data in motion is the live data that you share between publisher and subscriber, or that you reply to a query. Data at rest, because you may sometime want to store your data for a usage later on. So that's when your publication is stored in some storages, it's at rest. And with query, you can do also perform remote computation. So you send a query for a server to compute something, and you get back the reply. And the goal of Zenoh is really to have all those patterns available for any distributed system, from tiny microcontrollers up to data center, up to the cloud. And to provide this in a location transparent way with high performance and distributed queries. So location transparent, meaning that as an application developer, you don't need to care where your data wheel is or where your server is. You just name it with a topic name or a key expression we name in Zenoh. And it's only at deployment time, at configuration time, that you will interconnect everything, but the protocol itself, the Zenoh protocol, will find always the location where your named data is. And Zenoh, on top of this, also supports shared memory with a new zero-copy shared memory that is coming with Zenoh 1.00, which have been released just a few days ago. So those universal abstraction in Zenoh, first, publication and subscription. So you may have, for instance, two peer applications. One is a publisher, which performs put operation. And one is a subscriber that declares a subscriber. So by default, it can be a subscriber with a callback. So the callback will be called by the middleware, but it can be also a subscriber in pull mode. So it will consume the data at its own pace. So maybe sometime dropping some data if the publisher is too fast, but the subscriber can just pull whenever he wants. At the bottom, you have also the query pattern. So in Zenoh, it's a get operation to send a query, and it will go to a queryable. So a queryable is something that you implement at your application and has a callback which receives the query, and you can reply, send one, more, two or more replies for one query. And with those two abstractions already, we can build on top of this. So for instance, we added on top of this a storage example, storage notion in Zenoh. And what is a storage? It's really the combination of a subscriber, which subscribes to some publication, stores those publications, and then a queryable that is able to reply to queries later on for applications that would like to query some data from the storage. And all of this, of course, is with location transparency. So the Zenoh protocol itself is written, the core is written in Rust. We have an API in Rust, but on top of this, we implement different bindings for different programming language like C, C++, Python, TypeScript. Soon we will consider C#. Recently, we added also Kotlin and Java. And for the transport point of view, all that Zenoh protocol need is some transport able to transfer one bunch of bytes, so a byte buffer from one point to another point. Zenoh will take care of all the MTU limitations, so it will take care of fragmentation in case of big messages, recombination when those fragments arrive. It will adapt to the MTU, and it will also perform automatic batching of small messages, which is something quite important to improve throughput and to optimize the bandwidth usage, meaning that if you have a lot of small messages sent by one application, Zenoh will, as much as possible, try to pack them in a bigger message to be sent over the wire. So with support on data link, it means that Zenoh can be implemented on different transports, such as TCP, UDP, QUIC, or even serial communication, Bluetooth, Unix socket. And of course, we have also shared memory, which is a different kind of transport. And the protocol, we try to make sure that it's quite efficient on the wire, meaning that we were looking to have a minimal overhead of just roughly 5 or 6 bytes, depending the use cases. Is there any questions so far?
I do actually have a question. I'm very curious to hear more about your TypeScript JavaScript implementation. I looked at Zenoh quite carefully when I was choosing MQTT for the data layer in transitive. Mm-hmm. And I wished I could have used Zenoh at the time, but there were a couple of things that were missing. One of them you already addressed, which is the queryable and the storage. But I also at the time didn't see native JavaScript bindings. Is this now a first-class citizen? Do you support that yourself, or is it a community library?
So not yet first class. It's there is a development in progress, so it has not been released for V1, but it's ongoing. There is already a repository, open source and public on GitHub, for which you can already test it with the Zenoh V1. So hopefully we will work more on this in the coming months and release it as an official Zenoh API in the coming months.
So it's not quite ready for production, it seems?
For production, not yet. Well, it has been tested for most of your use cases, but it has not been tested at scale and with regard to performances. So
okay, thank you so much.
I will say you wait a few weeks if you want ready to have a production, but you can already test it to check if it's sweet for your use cases.
Thank you.
So another advantage of Zenoh is the topology in which it can be deployed. For instance, in this graph, you have several entities. The peers and the clients on one side are your application. Your application you can configure as a peer or as a client. I will explain what's the difference just after. The router is a software router provided by Zenoh, so it's just a process that you can deploy anywhere. So with this, Zenoh can support peer-to-peer communication. So all peers are connected to all other peers in a click fashion, but also in a mesh topology, meaning that all the peers are not directly interconnected with each other, but one peer can route all the publication or all the queries to another peer in case they are not directly connected to each other. The client in Zenoh is a more lightweight application in the sense that it will have only one connection, and it will not perform any routing. So in that sense, it's configured with more lightweight because it doesn't embed all the routing tables and the routing algorithm for Zenoh. So it just, for instance, if you have a web application or phone device, an Android or iPhone device, typically you will configure it as a client to be connected directly to a router or directly to a peer. And then we can, with the Zenoh router, we can support brokered communication. So all the clients connected to a router or to more than one router. And then the router can be interconnected to forward data between peers and clients and so on. So you can really build very complex systems, but also very simple systems. And all of this is just a matter to change the configuration. Usually you don't need to change your code because your code doesn't need to be aware of any location or any IP address or transport or whatever. Just to put this topology in perspective, in DDS, for instance, it supports only peer-to-peer communication with a plain standard DDS. MQTT, it's brokered communication. All your client needs to connect to a broker. This broker in MQTT, in some MQTT implementation, might be redundant. You may have several brokers. Usually, it's a pattern of master and slave. You have one master, and then the other brokers are here as a backup. And but with Zenoh, all the routers are equal. There is no real state, right? So if they are fault tolerant in the sense that you can connect one peer to different routers, and if one router fails, the communication will automatically fall back to the other router, and there is no notion of primary and secondary router here. They are all configured in the same way. And the same, for instance, with MQTT, usually when you have a cluster of brokers, they are all in the same layer, either in the cloud, either in your local data center. But it's sometimes very hard to have a cluster which mix broker in the cloud and broker in a local data center. With Zenoh, it's totally possible. You can deploy several routers in your local data centers, several routers in the cloud in different regions of the cloud, all interconnected together. And Zenoh will perform all the routing algorithm between all the routers and all your applications. With regard to performances, so we have some users making some testing. We are doing our testing by ourselves, but here, for instance, is a benchmark from NTU, Taiwan University, and it's not a recent one. We didn't make yet a benchmark for 1.0, but for the I think in 1.0 we have again more improvement, but this was with 0.10, and with version 0.10 we already on a 100 gigabit network almost saturate the network with 8 kilobyte payload. So it means you can see with small messages we have 5 million messages per second, depending the flavor. So in blue, the light blue curve line is peer-to-peer communication, and the purple one is with a router. So you can see the impact of having an extra hop, let's say, between two peers When you have a peer, router, peer, that's you lose some million of messages. But still, you get better result than with DDS, with Cyclone DDS, with Kafka, or with MQTT. For the latency measurement we made so far are around the microseconds, tenths of microseconds of latency in the middleware itself. So the latency measured on a loopback, for instance. So mainly what will matter with regard to latency will be the latency of your transport, which latency you get with the cloud, for instance. So in addition of this, Zenoh provides some plugins. Plugins for Zenoh are shared library, which are implemented in Rust, and that can be loaded at runtime by a Zenoh router or by an application. In recent Zenoh version, even a peer or a client can load a Zenoh plugin. So on one side, we have Zenoh plugin for the storages, so that all the databases that we support to store your publications and to retrieve your publication from storages, so InfluxDB, RocksDB, just main memory or just file system, and we can expand on other databases. On the other side, we have protocol plugins, so interoperability, well, bridging with other protocols like DDS, MQTT, or ROS. That's one of the main plugins which is used right now with the ROS community. It's a ROS 2 plugin. And actually, for instance, here is how this ROS plugin is working for Zenoh. It's really a mapping between all the pub, sub, and service and action from ROS on one side and the Zenoh pub, sub, and queryable on the other side. So, for instance, here we have an example of Turtlebot 4 use case with ARVs, which is remote. So it can be on another laptop in the same Wi-Fi, or it can be in another country just interconnected by the cloud via Zenoh. But still, the plugins are behaving the same. They are mapping ROS publication over DDS to Zenoh publication, subscription to Zenoh subscription. And the service are mapped to Zenoh queryable on queries. And same for actions. Action is a bunch of 3 queryable plus publications, and that's mapped in the same way. So that was the very first plugin we made for ROS. For us too, which was working, which is still working for Humble, Iron, and JZ. We are still supporting it. But more recently, you may have heard that we started to work with Intrinsic on RMW Zenoh. And actually, we made a presentation at ROSCON 2 weeks ago on the status of this new RMW Zenoh. So first, what is RMW? It's RMW stands for ROS middleware. So ROS 2 has a modular architecture, meaning that you can switch, you can change the middleware which is used by your application. So here you have a view of all the stack. On the top, you have your application, which are developed in various languages. So relying on RCL API, which can be in C++, in Python, in Java. Below this, you have a common RCL API in C. And this RCL API relies on a RMW layer, a first abstraction of a middleware, which then can be bound to different DDS implementation or no to Zenoh. So we developed with Intrinsic RMW Zenoh, which rely on Zenoh in C, which itself rely on Zenoh in Rust. And it's supported now in Iron release and in JZ release and in rolling releases. So the mapping we did for ROS to Zenoh in RMW is the following one. For encoding, it's still the DDS CDR encoding. Why? Because this way we can keep all the code generation toolchain which are already existing with ROS. So the parsing of messages, server, actions file, generation of IDL, parsing of IDL, and generation of serialization code in C, C++, Python, Java, and so on. For the publisher and subscriber in ROS, they are simply mapped to Zenoh publisher and subscriber. The service server and client are mapped to Zenoh queryable and querier. And the actions and our parameters are unchanged because anyway, they are not implemented on RMW layer, they are implemented on RCL layer. So on top of using 3 services and 2 topics for actions, for instance, parameters are using services. And for entity discovery and ROS graph, we rely on a specific Zenoh feature, which is named the liveliness token. So what is a liveliness token in Zenoh? It's just a simple declaration of a string, a key expression, we name it, which declare whatever the user wants. So for ROS, it's a declaration of a node, of a publisher, of a service, of our action. And then any other node in with RMW Zenoh can subscribe to this liveliness token and then discover all the declared nodes, publisher, subscriber, and so on. The benefit with the liveliness token is that they are bound to the session declaring the liveliness token, meaning that as soon as the connectivity is lost with the session declaring the token, all the subscriber of liveliness token will get the information that the liveliness token is gone. And it's very fast in a couple of milliseconds, depending the time of detection of connectivity loss. So it's very lightweight and reactive, and actually it solves a lot of issues that were existing with DDS discovery, which can be sometimes very heavy. You may have experienced this on Wi-Fi or over the internet with DDS. So what pattern of deployment have been chosen by default for ROS? Because Zenoh can support several patterns, as I explained. But out of the box, Open Robotics wanted to have a very easy out-of-the-box experience for most of the users, not having the past troubles with UDP multicast that might not work very well in some Wi-Fi, for instance, or even in some containerized environments. So by default, the configuration chosen for RMW Zenoh doesn't leverage UDP multicast. It leverages a Zenoh router deployed that shall be run at in the robot. And this Zenoh router is listening on the port on TCP on port 7447. And all the nodes are automatically configured to connect via the loopback on TCP to this Zenoh router. And the router will act as a broker for endpoint discovery. So in a similar way than you used to have in ROS1 with the ROS core. So it will exchange all the IP address and port number of all the nodes with each other. And the nodes will automatically establish peer-to-peer connection via the loopback. That's the default communication. Still, you can interconnect with other platforms, other robots or a controller host on your laptop, for instance, over Wi-Fi, just by configuration of the router. So all the external communication will be made by the Zenoh router via the transport you configure. It could be TCP, TLS, QUIC, whatever. The benefit of this is less connections. There is only one connection between each host. No longer peer-to-peer connections between all the nodes in different hosts, which can cause a lot of troubles to Wi-Fi. The batching, you can benefit the automatic batching from Zenoh, because if you have several nodes publishing small messages, Zenoh will batch them all together in a single connection to a remote router, for instance. You have a smaller surface of attack because there is only one port which is open for the Zenoh router. So you can configure only your firewall in your robot if you want. And the Zenoh router is a single point to also configure access control and downsampling. So downsampling is the possibility, for instance, to configure a high frequency publication to be downsampled when routed over Wi-Fi. So it means you can keep your 200 Hertz publication internal to the robot, but over the Wi-Fi, it will kill your Wi-Fi. So you can, for instance, downsample it to only 10 Hertz, and the Zenoh router will drop the extra messages when routing over Wi-Fi. So lot of questions about the router. The question we had so far is it similar to ROS1 core? Yes, it's similar in a sense because it's a broker for discovery and the nodes are communicating peer-to-peer. But it's more. First, it's more robust because when the Zenoh router is stopped or crashed, you can restart it. The node will automatically reconnect. And if during the crash period, anyway, the nodes are exchanging peer-to-peer, so there is no effect at all on your robot, right? All the nodes are working as usual, and you can restart the Zenoh router. It will resume its work for external communication. So anyway, for the graph cache, the ROS daemon is still present, so it can reply to all the ROS2 topic list and so on. Is the router mandatory? No, you can also change the configuration of Zenoh to use UDP multicast discovery, for instance, or to statically interconnect all your nodes, or to have a remote node to connect directly to the router, or to connect directly to a node in your robot. It's up to you. You can change the configuration in various ways for interconnectivity. And how to do this? Two configuration files. There is one configuration file for the node and one configuration file for the router. You can see the default configuration file in sources inside RMW Zenoh code. Those configuration file can be configured via two environment variables, one for the session, for the node, which is a Zenoh session configure. Usually, you don't need to change anything here. They will automatically connect to the router and communicate with together via the loopback. And then you have the Zenoh router configure for the router configuration, and that's where you configure all the external connectivities, the TLS keys and certificates, access control, downsampling, everything that is required for external connectivity. So here, for instance, we have an example. So that's an example we made for the ROSCON talk. So with my colleague from Intrinsic, Yadou, he had a Turtlebot running in California. I was in France. And you can see here, I was sharing my screen on the laptop via Google Meet. So the Turtlebot was running a Zenoh router, which was connected to another Zenoh router deployed in AWS EC2 instance. Just with an outgoing TCP connection. So no TLS configuration here. It was not really secured, but just for the first test, it's a good one, a simple one. You just need to change your configuration of your router in the robot to say connect to endpoint and the IP address of the router in EC2 and the port 7447. On my laptop, exactly the same config. Outgoing connection to the TCP to the router in AWS EC2 instance, and automatically on my laptop I can start RVs. I get all the topic information. I can do a topic list, and here you can see I can also access to the navigation stack, do a pose estimate, and send a navigation goal from France to California just with RVs. For secured communication, you can also configure TLS. So for this, for instance, you can configure a more advanced endpoint. So it's just a matter to give the name or the IP of your router in a cloud. So here it's in a Zeta platform. I will just explain after what is the Zeta platform. But what you just need to change is TLS configuration part, where you configure all the certificates, the root certificate, the client certificate, the client private key, if you want mutual authentication. Zenoh support mutual authentication, so you can configure authentication for your client. And in the same way, they are just connecting via TLS, via a router configured with certificates and security. Any questions so far with regard to cloud connectivity and what you can do with RMW Zenoh?
I'm just curious if how the Zenoh routers discover each other. So if you have, I can see on your list there you've got an endpoints list with a specific URI.
Yeah.
I assume that if you add more, then it provides more routers. Is it possible that you can provide just one, and that one has a list of other routers that you don't need to know about?
So yes, that's possible. As I mentioned, so Zenoh supports what we name the gossip protocol. So the gossip protocol is a way to exchange all the endpoints that have been discovered amongst each other. So you can configure the gossip protocol also for the routers, and to configure the router to auto-connect to any routers that have been discovered by gossip protocol. That's possible.
That's great. Thank you.
Maybe. And aside gossip discovery, Zenoh also supports multicast discovery, for instance. So, for instance, you could also have in a LAN, for instance, where UDP multicast is supported, you can configure the Zenoh router to perform automatic discovery over multicast and auto connection over multicast. That's something that might be useful sometimes.
That was actually another question of mine. So I think you've just answered, but the question was going to be, can you mix multicast discovery and your router discovery? And yes. The answer is yes. So you can put a Turtlebot up and make it multicast discover a router that has a fixed endpoint in the cloud, for instance.
Absolutely, yeah. So knowing that, of course, if by gossip protocol, your router in your local LAN, for instance, it will probably run on a private network, right? So the gossip protocol, of course, will not work if you send a private IP to a router in the cloud that cannot connect back to your private network. Right? You see what I mean?
I do, yeah. So if your Turtlebot has a private IP and that gets shared with the cloud server, it's not going to be able to communicate.
Yeah. Well, it will be able to communicate with outgoing connection, but it will not be able to communicate with ingoing connection, right? So it means you have your Turtlebot connecting to a router in the cloud. It can communicate with the router in the cloud, but it can discover another router in the cloud. So the Turtlebot will get the public IP of the router and can connect to the router in the cloud. But the router in the cloud will not, even if it gets the private IP from the Turtlebot, will not be able to establish the opposite connection, let's say.
So it functions as long as the Turtlebot establishes the session.
Yeah. But as anyway, TCP connection are bidirectional, it's sufficient to have one TCP connection. Everything is working.
That makes sense. Thank you.
No other questions so far? So I just have a few slides left about the Zetta platform. What is exactly the Zetta platform?
So I'm curious about, thank you for sharing about the client certificate. That was one of my questions. So that's the authentication.
Yeah.
I'm curious about the authorization. In MQTT, it's very typical to have patterns where clients have access to certain topics, but not others. Do you, maybe I should explain a little about my use case. In Transitive, we have a very fine-grained control over the types of clients and the topics that they access. And there's almost a one-to-one mapping between the name in the SSL certificate and the types of topics they can access. And this is because we namespace both by user, by device, and by capability that they use. And that is very important to us to make sure that the right people have access to the right things. And the way that we did that is through a custom Mosquito plugin into MQTT, which we really had to implement something in code. So my question, I guess, to you is, well, number one is, how do you do authorization? I pulled up the page and I just glanced at it. It sounds like you do have the topic-based one, but do you also provide the ability to specify custom authorization plugins in any shape or form?
So first, with regard to access control, we support access control based on named certificate. So you can provide your access control. You can configure the Zenoh router or even directly the session in your node to perform access control based on topic plus named certificate. So subject name. Access control is in Zenoh is made by the mean of some is implemented by the mean of some interceptors, and but those interceptors are not open. It means unlike MQTT, we don't have yet the possibility to plug custom code to perform such custom access control. So the only access control we have right now, I think it's equivalent to what you're currently using with MQTT, which is based on topic name plus subject name for certificate. That's already supported.
How does that work when I'm assuming you support? I believe you have WebSocket connectors in your list of possible. With WebSockets, you don't typically have a client certificate. How do you authenticate there, and how do you authorize them?
So in top of certificate in Zenoh, you can also configure a user and key on user password connectivity. So in the same way that you have in MQTT specifying for a client a user and network name. I'm just not sure if access control at this stage is able to use the username for such a rule. I need to check this, but if not, we need any way to enable it, because yes, you're right. In some cases, you don't have a client certificate, but still you need to be able to authenticate a client and to apply access control rules. So you could already leverage the client password functionality in Zenoh, which can be in addition of TLS communication. I just need to check if access control will work with this.
Okay. Yeah, one thing that I found very useful is to use JWT, so JSON Web Tokens, together with the WebSockets. And then the way that we solved it was we actually send a JSON Web Token as the password on the WebSocket connection, and then from there it goes into our custom plugin where we first verify the JWT, the signature, and then take the payload and based on that give access control. And this is a pattern that I personally love. I think it's very cool. So if you're still thinking about how to do that, happy to chat more about it. But this is a path that I really like.
Okay, yes, that's a nice idea, and yes, happy to get in touch to know more and to see, because yes, we don't support JWT for the time being. That's something we think about, but no implementation, no plan so far for it. But yes, if you have some requirement of some use case to share, we'll be happy to discuss. Yeah.
Thank you.
So just last few slides about the data platform. So what is a data platform? To manage Zenoh infrastructure, you need, in the cloud at least, you need to deploy some router and to configure all the interconnection between each other. You need also, if you want security, to configure all the certificates, the access control, the plugins, the storages, and then later on you want to monitor all the status of what is connected, all the connectivity between each routers, between peers. You want to monitor the traffic and so on. That's could be cumbersome as an application. So we provide, as ZettaScale, we provide the data platform, which is a platform as a service, where at first you can configure what you would like to deploy in your system. So you can configure a router to be deployed in the cloud. So for the time being, we support AWS as a cloud provider. We might expand later on. So you can configure instances, so it will be EC2 instances provisioned for you to run a Zenoh router with various sizes. But you can also configure a router to be deployed on your premise. And for this, there is no need of agent to run on your premise. It will just generate for you all the deployment file and configuration file certificate for you to run your router where you want on your premise. So, for instance, this is what you get after deploying a project with Zeta Platform. You can download certificates and configuration file for Zenoh directly from the platform and apply them. You can first test those configuration files with a simple Python script just to test the connectivity, but then you can apply those configuration files to your own application to be connected to the cloud or to your local router in premise. And then you can monitor everything directly from the cloud. So here we have a snapshot of the dashboard that the Zeta Platform provides. You can see the two different regions here, one in North Virginia, one in Frankfurt. You can see there are routers deployed in those two regions, one in North Virginia, two in Frankfurt. And you can see remote application connected. So here we have a teleop application on a robot application, for instance. So we can see all the interconnection between those, what they are using as transport, TLS, QUIC, or plain TCP, secured or not. And in another dashboard, you can monitor all the connectivity, so the metrics of your project, what are the throughput which are used, the usage of bandwidth for administration, for publication, for requests, for replies, in various formats, in cumulative, and so on. You can also monitor all the key expressions. So the key expressions are equivalent to topic name. So you can see what are used as key expression, if those are subscribers using those key expression, or if those are publisher or queryable, for instance. So here you can see an example. It's not using RMW Zenoh, but using the plugin for ROS2DDS. And you can also monitor some plugins that are used. So here, for instance, we have a DDS plugin, which is remotely monitored from the platform. And we can browse all the DDS participants, all the readers, the writers, the topics, and really have a complete view of DDS subsystems connected to a Zeta Platform. And for the future version, we will also expand to ROS2 using RMW Zenoh, meaning that you will be able to see the full ROS graph directly from the platform and to check which are the topic available, the node available in your system. So that's all for today. If you're interested in a few weeks or months, I can also organize a more longer meeting on the Zeta Platform to show all the possibilities from the Zeta Platform. And so, is there any question?
I have a question. Thank you for the talk, Julien. First of all, wonderful, very interesting. I wanted to know more about how you do. Do you do redundancy when you do cloud deployments, or do you need it, I guess, when you have just routed communication, right? When you're not doing peer-to-peer. And how do you do that?
So it's up to you to deploy several routers, right? With the Zeta Platform, you can, as I show in here, for instance, for redundancy, here in Europe, there are two Zenoh routers which are deployed in Europe. So you can deploy several and configure your peer application to connect to all those redundant routers all together. The peer application will only use one router for connection.
For the connectivity.
For connectivity.
And then the routing across among the routers themselves, I guess it's dynamically configured depending on these tokens you were talking about, whether that discover whether things are up or a router is down.
No, it's not related to tokens. Tokens are for ready for the application discovery. So the router have their own mechanism, which is based on what's the name already? Link state protocol. So it's really computation of routing tree based on link state protocol that are done amongst all the routers.
Okay, so then because I'm trying to think exactly how you deploy it on the cloud in a resilient way. So, but you were mentioning you would have the clients, the robots outside of the cloud connecting to one router endpoint. Then you can have a resilient network of routers within the cloud. And then what happens if the router you are connecting to from the robot goes down? The best way is to configure the robot to connect to more than one router, or how would you make that resilient? Yeah.
Yes.
So
the best way is to make your robot to connect to at least 2 or 3 routers.
2 routers.
Yeah.
Okay.
And if one fails, it will automatically switch to the second one. Yeah.
Excellent. Thank you.
Welcome.
This was.
I've got a couple more questions. One is about your storage plugins. I wondered if you can configure them to store particular topics without having to write code to do put requests or anything. So, for example, you understand.
Yeah. So absolutely. So here, for instance, in this example, you get some publication on a key expression, which is room/2/humidity, for instance, for some humidity sensor. When you configure your storage at deployment, you configure it with a key expression, which is to store everything that is room/***. *** meaning in Zenoh language, well, it's a recursive path amongst all the chunk in the key expression. So yes, in Zenoh there are two wildcard characters. The star will match only one segment between 2 slashes, and ** will match as much as segments that is possible. So here, room ** means we store everything that is published with room/ as a prefix.
And can you still do a direct peer-to-peer connection at the same time in parallel?
Oh yeah, sure. Yes, if here, for instance, this subscriber is subscribing to room/ ** and is connected to this peer, the publication will go on both this router and to the storage.
Right, but your peer that's getting, so the peer that you're already looking at, your arrows over the diagram, that data is going through the database, right? So, yeah, that diagram. So the data is going through database, which presumably introduces latency?
So no, it will not go through the database. It will be there will be 2 publication of messages, let's say. The message will be, if you are in peer-to-peer connection, the message will be published twice. Once for the subscriber here and one for the storage. If you have a router in the middle, it will be published one to the router, and then the router will republish twice, one for the subscriber and once for the storage.
Okay, no, I think that's what I was asking, and it sounds like you do support that, so that's great. And my last question, which is slightly off topic, but it's a personal passion of mine. How is it developing in Rust?
It's very nice. No, honestly, it's hard to dive in when you come from other languages, because there are a lot of constraints that you block on, starting with lifetime management, so which sometimes can be hard. But honestly, the Rust compiler is very nice because you get very explicit error message. And once you manage to make your stuff to compile, it's working. Except, of course, with regard to race condition, if you do multi-threading, multitasking, asynchronous code, you still may have troubles with regard to race condition, mutex, deadlocks, and so on. But with regard to management of memory, there is no longer any issue.
And was it painful connecting to ROS2 with that? I know ROS2 is very C++ based.
So yeah, it was. It's more challenging in the part. So I mean, the C and C++ code of RMW Zenoh is still need to have a mutex, to have a memory management, and so on. because it's based, even if the Rust core is Zenoh core is in Rust, still there is some C and C++ code that need to have its own mutex, its own memory management, and so on. Yeah. So there is no change on this aspect.
That makes sense. Thank you. I think Giovanni's just put his hand up, so I'll cede the floor.
Yeah, just another question that came to mind, because I remember the pre-RMW implementation of Zenoh that had this really cool feature that you could basically put a namespace in front of a robot and say, all the topics that come from this robot have this namespace in front. Is that preserved also in RMW, or?
No, no, it's not. No, it's no longer available in RMW Zenoh, because the Zenoh router is really ROS agnostic, right? So there is no feature that make it possible to add on the fly a namespace in Zenoh key expression and so on. So that's something which unfortunately is not yet. So we might, I don't know, we might try to find a solution. We need to discuss with Open Robotics about this. Yeah.
It's okay. I mean, it's not such a bad news. For me, it just means that all the effort I have put to put all the namespaces in front of my robots are for something at the moment.
Unfortunately, yes. With RMW Zenoh, you still need to set namespace for all your nodes. Yeah.
Thank you.
So thank you all for your attention and your questions. And yes, if you have any question in the future, feel free to ping me. I'm available on by mail, by Discord, yes, Christian?
One last one that I think is on everybody's mind. Do you have any insight as to, so I think right now if people want to use, as a RMW and ROS2, they still need to compile it from source or something like that. Do you know what the roadmap looks like for getting it into the binary release?
So we just released Zenoh 1.00 2 weeks ago. Open Robotics and we at ZettaScale are putting effort to port RMW Zenoh to this 1.00 version. I think once done, the plan is to, and once there is enough confidence that all the testing are passing, there will be a release. So I will say by end of the year there shall be a first release for RMW Zenoh, for Iron and for JZ. The long-term roadmap is to, anyway, Open Robotics would like to have RMW Zenoh supported as tier 1 for Kilton release. That will be next year. So we are putting effort to make it pass all the system tests. So we have CI right now running all the system tests, the navigation to tests, the iRobot tests, various performances tests. We are working on this. We need also to add security, SROS support. So all the mapping of SROS to Zenoh key management and access control. That's something we need to discuss with a secure working group. And the last one is Windows support. So it's already is supporting Windows, but there are more test failures we need to investigate before being able to claim we are tier 1.
Great, thank you.
Okay, great. Thank you. From everyone here, thanks for taking the time to present to us. I have recorded. I will be uploading to YouTube, so anyone that missed some or all of the meeting will be able to get that back. The link will be available on the site I just posted. That's the Cloud Robotics Hub. Also shows our upcoming meetings with hopefully more guest speakers in the future. Also, it will include recommended resources from the group. So next meeting will be in 2 weeks. There's currently just a general meeting planned, general discussion. Everyone is welcome to come along. And that's it from me. If there's any other questions, we have 3 minutes left. Otherwise, we can jump off the call. I think that's a lot of quiet. So I'll take that as we're ready to go. Thanks again, everyone, and see you next time. Bye-bye.
Thank you. Bye,
Thank you.
guys.
Thank you.
Bye.
Bye.
Thank you.